just an opportunity to brush up few things. Okay. Okay. So vector space is something we defined in the last class. Vector space is a space where if you take any two element and add them, so addition is defined obviously. So if you add two vector, then the result is also in the set V. Okay, and then if you take a vector and multiply it with a scalar C, then the resulting vector C times X is also in the vector space V. Okay, so this is the usual definition of vector space, and with these two definitions, we have few more consequences like here. So like this is already coming from the definition of the vector space, and you have commutativity, distributive, and so on. If you add with a zero vector, then it doesn't change, and if and negative is also defined. Okay, so negative is a vector such that if you add to X, it results in a zero vector. So and then other properties are defined, which I'm going to skip. Okay, these are like trivial things. So if V is a vector space and U is a subset of V, okay, then U is nothing but just a bunch of elements of V, okay, as a subset. If, however, U being a subset of V, and additionally, if U has the following, for instance, zero vector is in the U, for all X and Y in U, the sum is also in U. For all scalar C and X in U, you also have C times X in U, then U becomes a subspace of V. Okay, so then U also becomes a subspace of V. So a subset of a vector space is called a subspace of V if it satisfies these conditions. Okay, so actually it's a vector space in itself. Okay, it's an own space as a standalone. It's a vector space. Okay, there are like few things to like. It should have the same zero as the zero vector as the original space zero. Okay. Okay, so these are the things to. So it's automatically a vector space. Okay, so there is a question here. So consider the 4x4 matrix. U is a subset of R4, be the set of all X so that AX equals to 0. So the question is U a subspace of R4? Okay, so U here is defined to be set of all X, the vectors, okay, such that AX is equal to 0. Okay, so this is how the U is defined. So the question is, does U become a subspace? Okay, we are dealing with vectors in R4. So naturally this is in R4. So the question is, if you collect all those X for which A times X is 0, is this necessarily going to be a subspace? Okay, so that's the question here. It will turn out that it will be, because first criteria was that whether 0 belongs to U. Well, 0 belongs to U because A times 0 is indeed a 0 vector. So first criteria is satisfied, and second criteria of the vector space is if U and V are in capital U, then does this imply U plus V is still in capital U? Okay, so U and V belongs to U, then this means that AU is equal to 0 and AV is equal to 0. Then we check that A of U plus V is AU plus AV, so linearity of A, which is 0 plus 0, this is 0. So this implies that U plus V is indeed in U. And similarly, if U is in U, then any constant times U is also in U, because A times constant times U is nothing but C times A times U, but A times U was 0. So C times a 0 vector is 0. So this is indeed a subspace because it satisfies the the three conditions that we have listed in the previous slide. Okay. So now actually we can define something called null space. So the set of all u in Rn so that A times u is equal to 0 is called the null space of A. Okay, so null of A is the set of all u in Rn such that u is equal to 0. So this is how the null space is defined. So as we have proved before in the previous slide, null space is a subspace of Rn. Okay, so null space is a subspace of Rn that we have proved in the previous. Okay, so there is a proof being given here, which is what we did in the previous. Now the another question is, given u is in Rn, describe how do I know whether u is in the null space of A? Okay, so we have to check. So given u is in Rn, given u is in Rn, so A, how do I check whether u is in the null space of A? There we will plug in A times u, and if it is 0, then this implies u is in the null space. A other harder question here is describe all possible u for which A is equal to 0. Okay, that will be the null space of A. Okay, set of all u such that AU is 0. Now this is difficult. Like checking is easy. Someone gives you a vector, then it's easy to check. But if someone asks you to find all possible u such that A is equal to 0, that's a little bit harder question.
Sir, we can make a span.
Yes, we can make this.
We can find the span, right?
Yeah, span. Span of what, right? The question here is span of what you are asking for.
Yeah, we can find the span of null space. It's sufficient to describe whole of null space.
Yeah, so even the you mean the basis, right? So the correct way to say is the basis of the null space. So you want to find the basis B1, B2, whatever, Bk, and then once you have the basis, if you do a span of this, then span of that will also be in the null space. Yeah. So, but the question is like even finding the basis is not easy, right? Like what are the so basis is like the linearly independent. You want to find the maximal k linearly independent vectors, right? So, but how do you find even this, right? Maximal k linearly independent vectors. How will you find this? So this is a harder question. If someone gives me u already, then it's very easy to check. I do A times u, and if it's 0, then it's fine. But if someone asks me to find the whole space, it's a much harder problem. Right. So let A be this and u be this. Now it may be easier to check whether A times u is 0 or not. Right. So is u is in the null space? Just calculate A times u, and it indeed turns out to be 0. So this implies u is in the null space. Okay, so we did a matrix multiplication. There's just checking of that. Now the harder question, as we said, is describe all of the null space of A. Okay, so find u1, u2, uk, the basis, let us say, in null space, so that if you do a span of that, you get the whole of the space. So fancy description of the whole problem we know how to do, but okay, I mean this is like solving the linear system. So what you are really asking for is what are the all possible solutions of the linear system Ax equals to 0, right? All possible. So it's about characterizing all possible solutions to this. Okay, it's about characterizing all possible solutions to this. So if A is as I have described in the previous class, if you recall. If A is a non-singular, okay, non-singular, in other words, it's a full rank matrix, then solution to this is only x equals to 0. Okay, if A, the columns of A are linearly independent, then only solution I can expect is x equals to 0. Okay, this we discussed in the last class. If you don't recall, then you see this in previous videos, right? So in that case, if it so happens the columns of A are linearly independent, then only thing you can expect in your null space is the 0 vector. Okay, and the only way this is going to be other than the trivial 0 vector space is when columns of A are not are dependent. Okay, and it's a, and I'm talking about a square matrix right now. Okay, so so the one way is like if you have square matrix and then it's like not the columns are dependent, they have to be dependent in the square. In the non-square case, we already saw one example here. Okay, here we saw an example, and what do you think about this vectors? These vectors, are they dependent or independent? It's a natural question to ask is how, I mean, can I just by looking at this, can I just say whether they are dependent or independent? Okay, so one of the results we saw in the previous linear algebra class is if there are 4 vectors. Okay, so these are for vector number 1, 2, 3, 4. If there are 4 vectors in a 3-dimensional space, so these vectors are in R3 because they have 3 components. And if you put 4 vectors in a 3-dimensional vector space, they are bound to be dependent. Okay, because the basis of R3 is cannot be more than 3 because 3-dimensional. So basis can have only maximum. So any additional vector you're going to put is supposed to be dependent, supposed to be expressed in terms of basis, right? So just by looking at this, I can say, okay, this is definitely going to be dependent. Okay, so it's definitely going to be dependent, and hence in this case, what I can immediately say is that null space is going to be beyond 0. Okay, it's going to be something beyond 0, and that is what happened here. This is a vector that is not 0, but still it is in the null space. Okay, so this is still in the null space, and that is happening because of the linear independence. If it is not linear independent, then A times x equals to 0 forces x to be 0, because this is the same thing as saying x1 a1 plus x2 a2 plus xn an, where a1 a2 are the columns. Okay, so if this is linearly independent, then this we know that a1 a2 an vectors are linearly independent. Then this means that the only solution to this is x1 equals to x2 equals to xn is equal to 0, which means that x is equal to 0. Okay, so only solution to this is this. So we have done this before. Okay, so that's why these things are kind of related to each other. Yes.
Sir, I have a question on basis.
Basis, yes.
Sir, why does a n-dimensional vector space have only n basis vector? Why not n plus 1 or lesser than n?
Because those many only freedoms are there, right? So,
yes, sir.
Yeah, because only those many freedoms are there. Geometrically also we have seen seen before, right? So let us say this is like R2. Okay, so this is like R2, and then I know that the moment I have like let us say 2 vectors that we have seen before in the so I have 2 vectors and they make an angle, and that is done. That is enough for me to fill the whole of the space, right? So you give me any vector. So these are you give me any vector, and then I can fill whole of the space. Okay, so and a very basic thing to recall is like the canonical basis. Okay, if you don't care about the other basis, and since we are always in vector space of this form, it makes the life easier to understand. So why it's enough. Okay, so let us say in Rn, why only n is enough, right? In particular in R2, why in basis I have maximum 2, right? So I know that so because from the canonical basis, this is in R2 and this is in R2. OK, and what I am trying to say is that this is enough because I can express any vector using this only. OK, so you give me 2, 3. OK, so sorry, 2, 3 vector, and then I can write this as 2, 1, 0 plus 3, 0, 1. OK, so I never need anything more, and that is the basic thing about basis. Basis is like a minimum number of vectors you give me. That is enough. That is enough to express any other vector. OK, the moment because since these two in this case is enough, the moment I will put anything more, it will make this dependent. OK, it will make this dependent because any other vector that I'm going to put in here can be written as a linear combination of the existing vector. So this is no longer going to be linearly independent. OK, so it is built in the definition of the basis itself. That basis is the maximal linearly independent vectors that you can find in a vector space. So the maximal I can find in R2 is the 2 vectors that I know, and using these 2 I can express any other vector. OK, so that's the maximal I can find. That's why it cannot go beyond 2. Similarly, in R3, I need to express 3 degrees of freedom. So I need 1, 0, 0, 0, 1, 0, and 0, 0, 1. OK, again, I'm using the canonical basis, but it can be any 3 linearly dependent as long as they make some angle. I can express any vector. So in basis, that's the way basis is defined. That any vector, it's a maximal linearly dependent set of vector, and anything else can be expressed based on the remaining one. If it cannot be expressed, then that's not maximal, so it will contradict that fact. So that's how the argument goes. OK, so OK.
Yes.
Yeah, OK. So so the question is, how do I find the null space of A? Well, null space of A, it's like finding all possible solutions to the linear system. And how do you find all possible solutions to the linear system? Well, this is something you may have seen in previous linear algebra thing. Again, it's like you reduce it to echelon form and so on. So it's like you do row operations. You make this guy 0, you make this guy 0, and you update these rows using row operations. And then you make this guy 0 using this guy. So it turns out that this whole thing becomes 0 if you subtract. And so in this, you made this into an echelon form because the leading entry is 1. Leading entry is 1, and it is after the first column. And then the leading entry of the fourth is all 0. So that's it. It's nothing to do here. So this is the echelon form. And what are the free variables? These guys become free variable now, because now you can put anything on them, right? Why it becomes a free variable? Because now, if you remember, this is the matrix I have, right? So 1, 0, -1, 7, and 0, 1, 2, -3, and 0, 0, 0, 0. And the original problem you had was, let us say, x1, x2, x3, x4, and the right hand side was 0, 0, 0, 0. OK, or sorry, 1, 0. So if you write this down, then this is x1 and 0 times x2 minus x3 plus 7x4. This is 0, and this is x2 plus 2x3, and then minus 3x4 is equal to 0. And the last one is giving us 0 is equal to 0. So no problem. Now, why do you get into free variable? It becomes a free variable because I am allowed to choose 2 variables as arbitrary, because there are no constraint on that. Like no one is putting any constraint on me, because I can express x2 as minus 2x3 plus 3x4, and you can parameterize this. Choose x3 whatever you want, it doesn't matter. So x3 I can choose as t, so minus 2t plus 3, and x4 I can choose as s. Okay, so I can choose any of these t and s, and that is why it is called free, because I'm allowed to choose any. And once yeah, and from there I can also have x1. Okay, so x1 again is like x3 minus 7x4. So this turns out to be x3 was t here, parameterized as t minus 7s. Okay, so you see your solution. Now looks like this. Okay, so x1, x2 is there, and then you have these parameters here, okay, which are free. So I have arbitrary choice, and that's the case where you have infinitely many solutions, because s and t could be anything. So with this choice, what I'm trying to say is that with this choice of x3, x4, where x3 is s, x4 is t, and x1 I have defined it here, and x2 I have defined it here. Okay, so with this choice, this will satisfy the equation. So there are like infinitely many solutions, and it's infinite because you had the free variable that allowed you to choose arbitrary s and t. So this is the way to solve. This is the way to get the null space. Right, so this is the way to get null space case. Okay, so let us see this. So sir, yeah.
Sir, how is it harder then?
How is harder? Yeah, so it is harder relative to the previous case, right? In the previous case, someone told you whether U is in the null space, then it is very easy to check whether AU is 0, right? And this is indeed harder because you have to do a couple of row operations and so on, and then you have to okay, parameterize them.
In the sense, is it NP hard?
Oh, okay. No, I mean, no, I'm not saying in terms of NP hardness, because these problems can be solved in polynomial. Some polynomial time. So it's okay in this case. Like, at most, I will need here n, and at most I will need n row operations. Operations will be n square, and the row operations I'm doing is like I'm nullifying this, and nullifying this, and nullifying this. Yeah, it could be n square actually. Yeah, so total operations you can wrap up at n square, and after that is easy part is the free variable choice. Yeah. So yeah, I'm not saying this in terms of the NP hardness and so on. Just from the calculation point of view, and you can wrap up in around n square. So it's not really, too much. Okay, so even from NP hardness point of view, okay, so it should be within polynomial. Okay. Okay, so this is the way, and these are the things we do, but okay, it's fine. So the way we can express this, the parameter s and t that I described, you can put 1 and 1 here, okay, and you can write this in this form, right? Because you can like write this vector. I said like s and t here, right? So this was my s, this was my t, and this is my s, and this is my t. So you can rewrite this, and eventually it becomes a span of this guy and this guy. Okay, so this is the vector that we are looking for. We have done some algebraic thing here, that we have split x3, x3, x3 as a vector. You put here, and x4 part you put here. Okay, and then you take out the s and t common, and that is how you get into the span. Okay, so you know now the way to actually construct the span. We are not going to use all this in detail, but I'm just doing this so that you relate many things. Okay, so And this is an efficient in the sense like no proper subset can ever span. So this is the maximal that you are getting. OK, anything proper subset of this, just this will never span whole of null space. OK, it will only give you a subspace of the null space. So the way that you get this is the full null space. So this is a question that you can try offline. I'm not going to do this now. OK, so this can be done offline. OK, you can do this offline. So we are thinking about vector spaces. So one of the important vector spaces is so-called the column space of A. And what is this? It is all linear combinations of the column vectors of A. So this is column space of A is nothing but the span of, because all linear combination is nothing but the span, right? And these are the column vectors of, so this is the first column vector, let's say. This is the second column vector. And this is the, so this is an m by n matrix, so there are n columns. So column space is a vector space. OK, and this is the this is how it is defined. OK, so there are like a couple of fundamental vector spaces. OK, so let me write down some couple of vector spaces how well you are familiar with. This is column space that I just defined. Similarly, I can define row space of A. OK, I can define column space of A transpose, row space of A transpose. There is something called Eigen space of A. OK, so it's like a span of the eigenvectors of A. OK, so there is also something called range of A. OK, so range of A. So these are the fundamental spaces, and they are actually, some of them may be actually related. OK, so we will come back to this, but these are the fundamental vector spaces related to matrices. OK, we will see some of these in the coming. So column space is the first one, which is just take linear combination of all the columns of A. OK, and so column space, so how do we know a vector is in the column space of A? Previously you were talking about null space, so you were talking about U is in the null of A. Yeah, I forgot, I think the null space, right? Yeah, so U is in the null space, then the way to check is that AU is equal to 0 or not. OK, now you are asking whether Y is in the column space of A. Then this is same thing as asking whether AX equals to Y has a solution. OK, so this is the same thing as asking AX equals to Y has a solution. OK, or another way to say is like, so Y, asking Y to be in column space of A is like saying is Y is in the span of A1, A2, AN. And this is the same thing here. In other words, does there exist an X such that if I do A times X, that will make it a span? OK, so A times X is nothing but the span of the, not span, but the linear combination. So it's like A1, X1, A1, X2, A2 vector, and so on. This is A times X. OK, so this is the same thing as asking whether Y is in the column space of A or A times X is a Y. OK, so it's very easy to prove that column space is a subspace. So the first property, if you recall, in a subspace is that 0 should be there. OK, so 0 is naturally there in the column space because I can do 0 times first column of A, 0 times second column of A, and so on, plus 0 times n. OK, and this does give me a 0 vector. OK, so column space of A was all possible linear combination of columns of A, and one of these is this linear combination where I choose all the coefficient to be 0. So indeed this has to be in the column space of A by the definition of the column space of A. OK, or another way would be to say is like multiply a times 0 and it is 0, right? For any y1, y2 is in the column space, I must prove that y1 plus y2 is in column space. So y1 is in column space of A. This implies what? This implies there exists x1 such that A times x1 is a vector here, okay? A times x1 is y1. Similarly, y2 being in the column space of A, this implies there exists x2 such that A times x2 is y2. Okay, so these two conditions come from the given condition here. Now I have to check that whether y1 or y2 should be in the column space for column space to be a vector space. So I will simply check A times so y1, y2 to be in the column space of A means that I have to prove that claim is that there exists x3 such that A times x3 is y1 plus y2, right? So can I come up with x3 such that A times x3 is y1 plus 2? Then I prove that y1, y2 is in the column space. Now what is y1, y2? Where y1, y2 is A times x1 plus A times x2. I can take A common. So this is A of x1 plus x2. So the x3 that I was looking for is nothing but x1 plus x2. So indeed this argument is also true. Okay, so this is what I derived. Okay, now the third one is for any y in column space of A and a scalar c. C times y is also in the column space. So y is in the column space, then we know that there exists x1 such that x1 is y. Now we have to verify that there exists an x such that, so there exists some x2 such that it becomes cy. Okay, so from here I know y. So this is c times ax1 and c I can move it behind inside. So this is a cx1. So the x2 I was looking for is nothing but c times ax1. Okay, which becomes cy. Okay, okay. So you can watch these videos if it is a little bit fast for you. You can watch these videos again. I'm not missing any argument here. Okay, okay. Yeah, so the easy question is describe column space of A. Then we can just do the span. It is not necessary that they are the basis. In other words, they may not be linearly independent. Okay, there may be a subset that you have to choose out of these that becomes a basis, may not be the whole. Okay, so yeah, so so column space is nothing but the span of the columns of A, but this is not necessarily an efficient description. As I said, they may be dependent. So you may have some redundant vector that you could have removed from here. Okay, so there may have been some redundant vector. Right. So like sometimes you may be able to guess what is that redundant vector. Okay, it's like sometimes like you may have to see, okay, whether this is a linear combination of this or some other way around. Okay, and this and so on. Okay, so you may have to sometimes it's not very trivial, okay, to know this. But in this case, we know that the first two vectors would suffice because it turns out that these guys are dependent. Okay, so these guys can be expressed as this. Like, can you see this? Well, like, is there a way to see how I can express one of these vector, let us say 3, 5, 13. Okay, using these two. So can you see how I can write 3, 5, 5, 13 using this 1, 1, 3 and 2, 3, 8. Okay, So what should I put as C1 and C2?
C1 is minus 1.
So C2 as 2 and C1 as minus 1.
Yeah, so C1 is -1 and C2 as 2. So with this you can check that says 4 minus 1 is 3. Okay, 6 minus 1 is 5 and 16 minus 3 is 13. Okay, so this works. Similarly, you can check that this can be expressed. So what it is trying to say is that if you just write span, that may not be efficient in the sense that there may be many vectors that are redundant. Like in this case, this was redundant, this was redundant. I can throw out, still the span is not changing. Okay, because some linear combination of this and this can produce this, and some linear combination of this and this again can produce this. So span overall didn't change. So that's why this is more efficient, and I cannot reduce this further. Okay, I cannot write this as a linear combination of this or vice versa. Okay.
Sir, now this span has basis, right?
Yeah, so in this case, this too will become a basis because this is the maximal. Okay, this is the maximal that spans this, and so that turns out that the column space of A is a two-dimensional. Two-dimensional in the sense like vector space dimensions. Okay, I'm not talking about R2 or something, right? You see the vectors themselves are in R3. Okay, but the dimension of the vector space is 2. So what does this mean geometrically, right? Geometrically, this means that this is some kind of a plane. Okay, some kind of a plane. It has to be some kind of a plane because it's two-dimensional. But it's like somewhere in the space, right? It's a plane hanging around somewhere in the space. So vector space dimension is 2. The vectors you are using may have all 3 components. It doesn't matter. So we may have all 3 components like this active. So 1, 1, 3 vector, and this is like 2, 3, 8 vector. So these vectors are in R3. This is in R3. But if you span this, they form only a plane. So vector space dimension they create is only 2 because you have only 2 degrees of freedom you can think of. Okay. So okay. So given U in Rm, U in column space, are there x1 to xm so that this, well, this, as I said, like this is same thing as like asking for a solution to the linear system. Okay, and how you will do it? Again, it's like we invoked what we have studied previously. Is like if someone is asking me whether U is in the column space of A, then I will solve a linear system with U as right hand side and find all possible solutions such that this happens, just like we did in the null space. And then later we write a span of all possible solutions we found, let us say V1, V2. And that defines an efficient way to write column space of A. Okay, inefficient way is that you just take a span of all columns of A. Okay, but that is inefficient. Right, that's what we are saying. An efficient way would be to find a reduced set, and again row echelon form will help you here. Okay, because in row echelon form you see what are the redundant columns to throw away. So for instance, if you want to see this in detail, then this is an example. You do row echelon form. Since the last column is not a pivot column, the associates, okay, so like this is a consistent system of equations because it is inconsistent when these two don't match, right? 0 is not equal to 0, right? So then it becomes in this case 0 is equal to 0, so it's a consistent, so solution exists. And so indeed you will be in the column space of A, and first 2 columns are the pivot columns. Okay, so the first 2 columns are the pivot column. This implies that the first 2 of the original columns, all the pivot columns you pick, and that will be enough to span span column of A. Okay, so that gives you the basis. So this is like methodological way to find a efficient way to find a reduced basis of this. So you pick all those columns with the pivot. So what are pivots here? 1 and 1. Okay, all the rows with the leading 1, and until when you can find. Otherwise, if you cannot find, then they will all become 0, 0, 0 at some point onwards. So you stop until the pivot and pick those columns. So this means that first 2 column, if I have chosen, that is enough to span the columns of, that is enough to span the column space of A. And you should pick the original column, okay? not this column. Okay. So there is the methodological way to find a column space of A in a reduced one. Okay, not just taking all columns of A, but a reduction if it is possible. Okay, so okay, now let me go through something called as linear transformation. So linear transformation is nothing but a function from a vector space V to the vector space W here. Okay, so it's like a function. The kernel of the transform is the set of all V such that TV is equal to 0. So now we are talking about functions that go from one vector space to another vector space. So far we are talking about vector space. Now we are talking about a function from one vector space to other vector space. And we define the kernel of the transformation or linear transformation is when TV is equal to 0. So set of all V such that TV equals 0. So kernel of T is the set of all vectors in V in the domain such that TV is 0. So that's called kernel. And similarly, we can define an image of the linear transformation as a set of W so that TV is W. Okay, so image of T is the set of all TV such that V is in V. So you take all possible TV. Okay, so this TV is in W. Okay, TV is in W, right? Yeah.
Is kernel of T the null space?
Yeah. So you're right. There is a correspondence. There is another view because we know that linear transformation. I think in the previous classes I have told you linear transformations are like 8x equals to. They look like this. Okay. So any linear transformation T from V to W is the same thing as TU can be defined as A times U. All linear transformations are nothing but matrix times the vector. Okay. And so there is equivalent definition for this, like one of you pointed. So this is the same thing as saying that that this is the null space of A. I mean, the kernel of T is nothing but the null of A. Okay, you have to know what is the matrix of transform. In this case, the matrix transform is A. So kernel of T is nothing but the null of A. In other words, what are the U's such that AU is 0. Okay, and same thing you can argue for the image of A. Image of A is the set of all AU. Okay, so you take all possible U from the vector space V, and you form all possible U, and that becomes your image. Okay, so there is a corresponding view using matrices. So it is easy to prove that the kernel of T is a subspace of V, and since we have identified that the kernel of T is nothing but the null of the corresponding matrix of transform, and we have already proved that this is a subspace, so there is nothing much to do here. Similarly, okay. Similarly, image is the subspace. Okay, so this also like it's fine. Actually, this is same as the column space of A, of the matrix of the transform. A is the matrix of the transformation T, right? So in some sense we have already proved this. So this is just a cosmetic proof right now. So nothing much here. Okay. So then the image, that's what I said just now. Okay, it's column space of A. So I will leave this proof because these are like trivial proof. You will see immediately from the slides. And this is also a question I can leave right now. Basis, I think definition I did not define yet, but actually now it's trivial now. Okay, I will skip these things because these are only independent and dependence things going on. So I can skip this. Okay, there is yeah, so we can see this theorem. So a set of vectors is linearly dependent if and only if some element is a linear combination of the other. Okay, that is by definition itself, right? Put other way, a set of vectors is linearly independent if and only if no element is a linear combination of the other. Okay, that's something we have already remarked. Again, I will skip this question. Yeah, there is another theorem here. A subset V1 to Vk that spans V is linearly dependent if and only if a proper subset spans V. Okay, so that's also intuitively clear. Like if there is a subset which is of V that can span V. So here it's saying span of V1 to Vk is whole of V. Okay, that spans V. This is the meaning of that. And if this subset is linearly dependent, then it must be that we can remove, let us say Vy was dependent. So we can remove that. Span remains the same. Okay, so then we can surely remove, if it is really dependent, then we can surely remove where those variables. If you could not remove, then it's independent. Right, so the argument goes both ways. So if it is dependent, if and only if a proper subset will still span the V, right? Or the same thing you can say in other way for independent. Okay, I can. Okay, so this is the definition of a basis. A subset this V1 to Vk is a basis for V if and only if it is linearly independent and it spans V. Right, so this is how the basis is defined. And another way to define a basis is like a maximal linearly independent set that you can find. Okay, that will define a basis. Okay, so both are like equivalent. Okay, so what we are trying to say is like so this is a basis because so first of all the span should, for any basis, the span should give you the whole vector space. So that is the first criteria surely. Okay, and furthermore this should be linearly independent. Okay, so VI's are linearly independent. So that's it. So that should form the basis for the vector space V. The usual ones are the canonical basis, like I said, 1, 0, 0. Okay, 0, 1, 0. So these are the canonical basis. They are denoted by E1, E2. So this is like E1 and this is E2 because there is 1 only at the second place, 1 at the first place, and so on. Any finite spanning set of vectors contains a basis. So that's also like intuitively clear, right? Any finite spanning set of vector will contain a basis because I can keep removing the dependent vectors and ultimately I will be left with all linearly independent. Okay, so these arguments are fine. Okay, I'm not going to. Yeah, so these are like just corollaries. And this is a question here. So consider a set of two vectors. There are three. So as I said, these are vectors in R2 and you have put three of these vectors. They are guaranteed to be dependent. Okay, so three vectors in a two-dimensional space, they are guaranteed to be dependent. So this is really a dependent. This set is really linearly dependent. So let us see what are the options. Which is the most informative to a student? The set S is a basis for R2. So do you agree that set S is a basis for R2?
No.
Yeah, because for a basis, it must be linearly independent, right? So clearly it is not a linearly independent set because just I said three two-dimensional vectors cannot be independent. So it is not, because for a basis the set S must have been linearly independent, which is not. Some proper subset of S is a basis for R2. Do you agree?
Yes.
Yeah. So indeed we can reduce the dependent one, right? So we can reduce the dependent one. For instance, in this case, I can remove this. OK, and then I see that these guys, furthermore, I cannot remove because I cannot write one as a combination of the other. So this will be the reduced case S hat 1, 2, and then 2, 1. So this so some proper subset of S indeed can be a basis. Each pair of vectors in S is a basis for R2. So if you pick any of the two, that will form a basis of R2. So do you agree with this?
Yes.
Yeah. OK, so the answer is indeed yes, because pairwise they are linearly independent. If you see these guys, I cannot write one. If you're comparing only two, then you just have to see a scalar multiple. So can I write 2, 1 as some scalar multiple of this? Definitely not. Can I write 2, 1 as some scalar multiple of 3, 3? No. OK, so can I write take this pair 1, 2, 3, 3? Can I write scalar multiple other? No. So they are pairwise. Any pair is linearly independent. So any pair, if I choose, it will form a basis. Every proper subset of S is a basis for R2. So do you agree with this?
No, because then it
No, sir.
No. So what could be that? So what could be the cardinality of the proper subset to as a counter example?
0, 1 or 2.
2 proper subset with cardinality 2, are you sure will not be a basis? Because just now we saw, right?
So proper subset with cardinality 2 will be a basis.
Will be a basis, exactly, because we just now saw, right? If I said take a subset with this 2 or this 2 or this 2, it is always going to be basis. Actually, those proper subset with cardinality less than 2 are the ones which are not going to form the basis. So for instance, 1, 2. Now, if I do a span of this, I'm not going to get R2 because I cannot produce vectors like 2, 1 using this. So it will not, it is not, if it was a basis, it should have produced any vector in R2, right? OK. So given a linear transform Rn to Rm with matrix A, so corresponding matrix is given to you. Find a basis for the kernel of T. Now, basis for the kernel of T, as I said, this is same thing as the null space of A. And what you are really asking for is the basis for the null space of A. So this question of linear transformation always boils down to matrix, if you can find the matrix of transform. And you can do everything like in the matrices that you did. OK, so solve AU equal to 0, see if you can find the free variables and write that using the span of those vectors using the free variable and so on. So we have done this. It's nothing but the null space, and we can safely skip this. And similarly, one may ask, what is the basis of the image of A? Well, we know that the image of the linear transform is nothing but the column space of A. Okay, this is nothing but the linear combination of the columns of A. And finding a basis of this, okay, finding a basis of this is like finding is like finding the reduced set if you can, because it may be that the columns of A are dependent. So this is already we discussed this. I should proceed it. So it may be dependent. So you have to just remove out some columns from here and make it a reduced one. And this, how do you do it? Again, you can use the elementary form that we discussed previously. Remember the place we were saying efficient span of column, and there's the same problem here. Okay, so that's what actually it's the same example being taken here. Okay, what is the meaning of coordinates, right? So people talk about coordinates in linear algebra, right? So there is a fundamental difference in the way you see coordinates, right? So let us say someone gives me the point 2, 3. So if I see the point 2, 3, so the point is here, right? Okay, so the point is here. So this is, and this also represents a vector 2, 3. Okay, so there are two interpretations of the points. So the way we see vectors is with respect to coordinates. Okay, we see vectors as coordinates, right? So what do I mean? Right, so this is, so for me this is like a coordinate with respect to some basis. Okay, so for instance, I can write 2, 3 as 2 times 1, 0 plus 3 times 0, 1. Okay, so what I'm saying is like I have to go 2 in 1, 0 direction and 3 in 0, 1 direction, and then I reach that point. And here 2, 3 are called the coordinates. So the usual way you see vector is the coordinates of the canonical basis, right? You write this as a canonical basis. Now if I change the canonical basis, the coordinates will change. Okay, so the concept of coordinate is how far I go in one basis, how far I go in another basis. That length is called coordinate. Okay, so if you have not seen this, then this is the how you should recall. When someone talks about coordinates, usually they are talking about coordinate with respect to the canonical basis. So they will say, okay, go 2 directions this way, 2 directions this way, and then you will. So the way you can reach some direction. Okay, so someone can point you. Someone can point you that okay, go in this direction straight, and then go this direction straight. So this is just one way to say that, right? But another way to say this could be is like go in this direction this much, and then go in this direction this much. Okay. So these two directions, if I pull them to the origin, then they look like this. But these are also a good basis for me, because I can reach anywhere. It's just that the concept of direction has changed, and also the length has changed. So the coordinate has changed because my basis has changed, right? So this now along this direction I may have to walk a lot more, and along this direction I may have to walk less. Okay, so amount I will walk is called the coordinate, and amount I will walk in this basis is the coordinate. Okay, so the idea of coordinate is so usually when we write 2, 3, we are implicitly assuming that it is the canonical basis. Now I could have other bases also. Let us say -1, 0 and 0, 1. Okay, so these two are also bases for me. Okay, in R2. So if I want to get to the point 2, 3, now I have to follow different lengths, right? So I now have to follow different lengths. For example, now, so 2, 3, the vector that you usually see with respect to the canonical basis looks different. The coordinates look different in the different bases. Let us say this is B2 and this is like the canonical basis is B1, because the same vector, the vector now looks different in different bases, right? Because now I have to do like let us say -2, and then I have to do 3. Okay, now like to go to 2, 3, I have to do -2 of minus 1 0 plus of 3 times 0 1. Okay, so the coordinates now are different now with different bases. So you see the concept of a point can vary depending on the which basis you are using. So for someone working with canonical basis, the point is 2 3, but the same point in the space, the definition of point changes. So this is like 2 3 with respect to the canonical basis, but the same point also means minus 2 3 with respect to other bases. Okay, so that's the main thing about coordinates. So if you change the basis, your coordinates change. Okay, so that's the big takeaway from here. Change the basis, coordinate change. Obviously, matrix of transform will change. So many things will change. Okay, so I think I can skip this. It's not that important for us. If you want, you can go through this and again ask the TS for more on this. I'm going to skip this. These are like some. These results are just like the usual results for the basis actually. So if v1, v2, vk is a basis, then there can be exactly unique coordinate. Okay, yeah, this is an interesting observation here. Okay, so if it so happens that your vectors are linearly independent, okay, and it is a basis, then your coordinate will be unique. Okay, otherwise you may find different coordinates for the same point. Okay, so that's the takeaway from here. Indexing matters also. Okay, ordering matters. Okay, even in the canonical basis, if you change the ordering, for instance, my basis is, let us say 1 0 0 and 0 1 0. Let us say R3 and then 0 0 1. This basis, the coordinate with respect to this basis will be different from the coordinate where I just interchange these guys. So 0 1 0 and 1 0 0 and 0 0 1. Okay, because in the coordinate we naturally come up with the ordering like this. So C1, C2, Ck. So if I flip one of my basis vector, although as I said they are same. Okay, remember as I said they are same, but even if they are like interchanged, these guys must be interchanged accordingly. So C2, C1 and then Ck. Okay, so the ordering matters for the coordinates. Okay, but obviously we know that trivially we consider like this 1 0 0, then 0 1 0 and so on. Okay, so like this is one example here you can think of where a vector b, basis b is given, and what is pi e root 2 with b. Okay, so b is these are the questions, right? So b is not a basis because it does not span R3. So is this correct? B is not a basis because E1, E2, E3 are not linearly independent, and this with respect to this basis, okay, which is this basis. Here
I can't see the slides.
Sorry.
Yeah, it's fine, sir.
Yeah, I mean, I'm a little bit not sure about this question because I don't see any change in the ordering also. And the question is asking pi e square root 2b. But this should be similar because there is nothing, no changes I can see. And this is okay, like, so B, I mean, this is false, like B is not a basis. That is false because E1, E2, E3 are canonical, that's fine. B is not a basis because this is not, that is also false, unless this definition is changed, right? But I don't think I've changed anything. This seems to be true. The information is not enough to decide. No, that is not correct. So you can, this is like, these are just canonical bases, so this will be same as this. Yeah. So answer C is correct. But I don't understand why, what is wrong here? No, this is false. Yeah, we also concluded this is false. Yeah, sorry. So we already concluded this is false. This is false. Only thing we said is this is true. This is false. We also came with the same answer. Okay, that's fine. Okay. Yeah. So okay, here let us say. Okay, here actually, this is the problem. Here actually the basis is changed, right? So there's some flip happened. Now this is going to be different now. Okay, because there is a flip here, right? So since there is a flip, now the coordinate will change because now you have to do the corresponding flip with the coordinate. Oh, not this one, but like the flip that happened was with this guy. The middle one remained the same. So you have to do a swapping of this and this, which is what is done here. So with the new basis, there is a flip in the coordinate. Yeah, that's the takeaway from here. Okay. Meaning order matters. Okay, so I can skip few things about the basis, like these are not really like, it's good to know, but not really terribly important for us right now. So yeah, so a few important remarks about dimensions and the rank. Okay, there is something called rank nullity theorem. So that those few of these things we will need also in the class. I will skip these basic things. You can go and look into this and revise and ask questions with the TS. I can tell you these are like okay. Let me skip this. Let me skip these things. Yeah, important thing to remember is any two bases of the vector space should have the same number of vectors, and this you can prove with common logic. Okay, there's no big deal here. The proof is very small. Okay.
So you go to the previous slide. It says dimension of n needs a basis of n plus 1 vectors. Yeah. What does Pn?
Oh no, here it's about polynomial, right? So if you want to denote a let us say 2-degree polynomial, that's the way I define. So 2-degree polynomials look like ax square plus bx plus c, right? So 2-degree polynomials.
Yeah, got it.
So in this case, in the basis, you need 3 x square, x and 1. So this will form the basis. So for nth degree polynomial, you need n plus 1 in the basis. Okay, so two bases of the same vector space must have same number of vectors. Easy enough. So dimension of a vector space is the number of vectors in the basis. Okay, and that is written as dimension of V. Okay, dim V. So any vector space, the basis number of elements in the basis will be dimension of the vector space. Supposed to be unique because any two bases have the same number of elements. Okay, so I can skip this. Yeah, these are less corollary actually. Okay, these are really corollary. Obviously, the dimension of the subspace will be less than or equal to the dimension of n of the original space. Okay, so that comes naturally. And if it so happens that the dimension of your subspace becomes equal to n, then this must be, then the space must be equal. There is also like a trivial result because you found n linearly independent vectors in your subspace U, and you know that dimension of your original vector space is n, so that should also act like a basis for your original space. because that's how it works. So any n linear independent vector will be a basis, and since dimension of V was n, that should generate whole of V. That's why U will become V. Okay. And then there are these things. Yeah, so now this is the question being asked here. What is the dimension of the null space of A? What is the dimension of the column space of A for this matrix? Okay, so we have done this example before. We had these two parameters, right? Free variables. So number of free variables tell us the dimension of the null space of A. Okay, so dimension of the null space of A would be 2 actually, from our previous working on the same matrix. So 2 free variables. Remember the null space for this example was 2 vectors using S and T. So those 2 became the null dimension of the null space. This seems to be possibility, and the remaining should be the column space of A. I mean, another way, the direct approach was that the pivot columns in the original matrix, you go and fetch those first 2 columns corresponding to the pivot. In this case is the first and second, and that will be the
third column is all, fourth column is also pivot, right?
No. Fourth column. Okay, let's see. Yeah. Fourth column is a pivot. Yes. Yes, fourth column is also a pivot, right? Yeah. So first column, second column, and fourth column you have to pick. Yeah, I'm mixing with this other example, right? Because this is also a pivot. So three in column space are there, and 2 in null space are there. Okay, actually it turned out that this was the D was the correct one, right? So dimension of the null space is 2, and dimension of column space is 3. So from here, what do we observe? Actually, we have already derived so-called rank nullity theorem. So from here, you can already check what is happening. So dimension of the null space of A plus dimension of the column space of A is what? Can you tell? Is equal to
number of columns.
Is equal to the number of columns, right? So A is, let us say, m by n. So from here, actually, you prove the rank nullity theorem. This is the well-known rank nullity theorem. Okay. So this is what this slide is going to show. So right now you have enough intuition to understand what is going on. So I can just tell you that this is what happens. Okay. The dimension of column space plus null space is the number of columns. Okay. In this case, number of column is P. So these are some examples, trivial example that you can work with. I am not going to. Yeah, so important thing to do is, I think I would have needed a little bit more time, but let us see. We still have 10 minutes. Let's see how far we can go with this. So the most important thing, I mean, one of the most important thing in linear algebra is the concept of eigenvalue and eigenvector. We have seen other things like determinant was important. Linear combinations, types of spaces we have in linear algebra. We have seen quite a lot now. Null space, column space, which is equal to the range space, image space. Now from here we will get one more space, which is the Eigen Space. Okay. So a linear transformation T may be complicated, but may look very simple on some vector. So what it is trying to say is that you may have a linear transformation that going from V to V, but sometimes the linear transformation can look very simple. It's just a scalar multiple of the vector itself that it is trying to map. Okay. In general, if you give a vector V, then linear transformation can do many complicated things to the vector. Okay, so it may change. Okay, sorry. Yeah, so it may. So I give this vector. Oops, this doesn't really. Okay, so I give this vector, but linear transform can make this into this vector. Okay, it can do some rotation, some elongation, and so on. So linear transform can do arbitrary things, but in some of the simplest cases, what it can do is it can only end up doing a scalar multiple. That is like very simple thing. So I gave this vector, and only thing it could do is like it could just prolongate this, let us say, or even like contract. So it could be just contracted the vector. This is what scalar multiples mean. So if there is a vector v such that TV ends up being only a scalar multiple, okay, of just a simple scalar multiple of v, then v is called an eigenvector. Okay, and the corresponding scalar lambda is called the eigenvalue. So in terms of matrix, it's like AV is lambda v. Okay, if you can find a pair lambda and v such that this happens, AV is lambda v, then we call v, the vector v, as the eigenvector and the scalar lambda as eigenvalue. Okay, that's how eigenvalue and eigenvector is defined. So v has a special property, that's what I said, its direction is the same, but only size is increased. Direction can be opposite if the lambda becomes negative. So that's fine, we call it same direction. Okay, just going in other direction is also considered same direction in our vector concept. Okay, so that's why it's saying direction is same, but a vector can go this way also if I multiply by -1, right? Okay. So lambda less than 0. Okay, that's what it's trying to say here also. Okay, so so what it is trying to say, if v is an eigenvector, then any scalar multiple of v also becomes eigenvector. So it again becomes some lambda times the vector in a scalar multiple of that vector. So if you do, if someone gives you an eigenvector, then you can generate infinite number of vectors. Okay, infinite number of vectors which are also eigenvectors just by taking a scalar multiple of that vector. You can ask, what about 0, right? But then 0 is not allowed as an eigenvector. You should always remember this. 0 vector is never considered to be an eigenvector. If you allow 0 vector to be an eigenvector, then you can get any number of eigenvalue, which will be absurd, right? Because 0 times any lambda will be 0, and that will make it absurd. Anything can be eigenvalue, right? So that doesn't help. So you take out 0 from the eigenvector. So what are the geometrical interpretation of the eigenvectors? Well, let us say if you do consider this shear matrix. So the intuition here is that in the shear matrix that we have seen, if you recall from the previous class, it was not rotating any of the vector along this direction. It was only changing vectors that has some vertical component, and they become like this. Any vector with even slightest of the y component, then it moves. But those who are exactly on the line, it was not changing those vector. Okay, so that's the shear matrix, if you recall, and this is the shear matrix example. So you can interpret this in terms of eigenvector. In other words, any vector which has only x1 component, for example, any vector that has x1 component, I can think of as well, just arbitrary x1, let us say, and this is 0. Let us see what it does to this, right? So this makes it how much? Okay, so this makes it x1, and this is 0. So it did not change, right? So these are all eigenvectors. This acts like an eigenvector of A with eigenvalue with eigenvalue what? 1. Okay, so with eigenvalue 1. So Shear matrix. So these are like geometrical interpretation of the eigenvectors. Okay, so some vectors are not changed by the matrix, or even if it changed, it is only changed by a scalar multiple. Okay, but in certain other direction it will change. Okay, so these things play a role also in the optimization theory. We will see later on when we discuss the optimization part. Okay, so for example, you can think of a linear transform, right? So if it is scaling in this direction, then it says that it has eigenvector in this direction with eigenvalue greater than 1. Okay, that is why any vector I'm putting it here, it is throwing it here. Any vector I'm putting here, it is throwing it here. So it's like, so this is like a circle is being mapped to an ellipse, and this is happening because one of the eigenvalue. So this is like an operator in R2, so the matrix will be 2 by 2. So this geometrically what we are interpreting is that there is one eigenvalue which is along this direction which is greater than 1. That is why any vector is getting stretched, and the other eigenvalue lambda 2 is supposedly in this direction and it is contracting. It's like less than 1. So vectors that were here are now mapped here, mapped here, mapped here. So it's a contraction. So elongation and contraction can be viewed as some eigenvectors. The operator has some eigenvalues greater than 1 in certain direction and some eigenvalue less than 1 in certain direction. These things play a very important role in optimization theory. We will see obviously in detail which are the preferred directions. You will increase a preference along certain direction so that you go quickly in the minima. Okay, that's a very top level intuition I'm trying to say, but don't take it literally. But the question is, when you are finding minima or maxima, the question is what is a good way to reach to minima or maxima? So what contraction of the space you want to do, okay, such that you move very fast to maxima or minima, and these things has a relation to that. Okay, so we will see this in more detail. So I think I have to stop, otherwise the video gets split. I will do, let us say, 15 minutes more of the eigenvalue eigenvector in the next class, and then we will really jump into optimization theory. A little bit of calculus will be needed, but that I will do it along the way. Okay, along the way when calculus, I mean usual things like gradient, Hessian is needed, I will do it along the way. But linear algebra is very important. Okay, so that's why I had to do this. Okay, with that I will say thanks, and let us do tutorial. So the tutorial will split into 2 groups, I think, and that's what my TS told me. So you can